Good day everyone, my name is Klaus-Dieter. I'm running the lab on materials and quantum beam science here at GTIT. So what we do is materials research with neutrons and synchrotron radiation. I'm interested, for example, in thermomechanical processing. This is the making and shaping of metallic metals. Basically, all engineering metallic materials are made via these processes. In particular, I'm interested to measure the structure of the material while we do the processing. And what we want to do is, we want to use a neutron or high energy X-ray beam to study the material while it's ongoing. Here on the example on steel making. To the right, you see the temperature. As it increases, we see changes in the microstructure, in the crystallographic structure. So now at high temperature we have an austenite phase, and even if we go higher to above 1700 centigrade, then we see the delta phase and large grain growth, which is nice to observe here. And as we go through the phase transformations, we can see the distortions of the crystals. Modern diffraction methods for the investigation of thermomechanical processes aims to explain novel methods in neutron diffraction, synchrotron X-ray diffraction, but also in data analysis. This is very important. Merge the disciplines between instrumentation, material science, physics, and engineering. Many students have been involved on-site in the experiments, here for high pressure or texture measurements. 2 years ago, while I was at GTIT, we went to the Spring 8 facility in Japan. Meanwhile, we have been back again, having a team here from Technion. So there are people from Technion, there are people from the USA, from Technion, and myself. At the time, I didn't have a student here. The synchrotron is a huge facility. It's built around a mountain, and there are many beamlines inside where we have the very sharp X-rays and the top beam qualities in the world. Another facility we went 1 year ago is the JPAC facility in Japan, which is one of the largest and leading neutron research facilities. And our team here, together with Professor Megumi Kawasaki from Oregon State University and her student, we are doing the experiment. From these rings and ring sections, we can read correlations of crystallites. We look to the individual spots on the rings. We look to the evolution of these spots as a function of time, which is shown vertical here, and can get information like grain growth, recrystallization, recovery processes, slip systems, but also something like strain analysis, where we can find load partitioning between orientation and lattice planes. You know, some lattice planes, they yield earlier than others. And on the other hand, we can look to highly frequency excited materials such as megahertz and 150 megahertz ultrasonic excitations. In this example of silicon or of piezo and ferroelectric materials. We have world-established research connections. If you join as a student, you certainly will join some of these connections, namely to leading synchrotrons. We're doing experiments at the Petra 3 beamline last year, 2020 in Germany, Spring 8 in Japan 2 years ago, ESRF in France upcoming, and APS in the USA waiting that the corona restrictions cease. Similarly, we are traveling to leading neutron sources, such as JPAC in Japan, which I just mentioned, Australian Nuclear Science and Technology Organization in Australia, the Institut Laue-Langevin ILL in France, and the Forschungsreaktor Munich in Germany. Of course, we have international collaborations with the Technion and also with Oregon State University in the USA. It's a very strong collaboration. Or even the University of Wollongong in Australia. And then we are represented in international societies such as the TMS and the MRS in the USA, Materials Australia, the Deutsche Gesellschaft für Materialkunde and Deutsche Physikalische Gesellschaft in Germany. I mentioned this international collaboration with Oregon State University. This is located in Corvallis in the USA on the West Coast. We have this collaboration with Professor Megumi Kawasaki on high pressure torsion. So this is where we put 6 gigapascal into this machine, shown to the left here, and refine the material to ultra-fine grained graded composite, make the material very strong and very hard. There may also be opportunities to exchange our research students and go there to the other side. Here I resume the interests of the research group Quantum Beam Science. We want to do advanced studies using synchrotron and neutron beams to perform in situ and ex situ investigations of materials under processing and making conditions, design of the alloys, materials under extreme conditions, following chemical reactions in real time and under real conditions. And examples are making better metals, that's what I have shown you, which are stronger, lighter. Then I'm interested in fast and ultra-fast real-time behavior of materials under external stimulation. This relates to the kinetics and the dynamic of functional and structural materials from the millisecond to the picosecond range, response to the materials of electric, magnetic fields, shock, current pulses, temperature, light, illumination, high frequency. And examples are piezoelectric oscillators and actuators, energy conversion and storage, and high frequency devices. And last but not least, we are interested in novel quantum beam methods and new facilities for material science. This is doing research with and development of quantum beam methods regarding opportunities. We have openings for master's and PhD students. One project I have in mind is on ultrasonic applications in material science, where we look to high cycle fatigue, ultrasonic strain and stress measurements, and ultrasonic processing. Then severe plastic deformation. This is the collaboration with Oregon State University. Here at GTIT we have local capabilities and equipment. First of all, we have 70 square meter lab space. We have the advanced X-ray diffraction lab. We have large computer data analysis because we have terabytes and terabytes of data. And we have an electronics lab, particularly a very expensive gigahertz oscilloscope for the high frequency studies. Desired skills to a student are the deep understanding of the materials physics, then computing skills. So you have to be interested in computers because we have huge amounts of data. Here on the side I show a computer program steering that stepper motor. You may have the ambition to learn new concepts, and very important to work in a team. With this I like to thank my actual team. You find more here on this given website. Beside myself you find Xiaoxing Liu, Xiaotong Cheng, Yiying Xu, Shuai Xu, and an Israel co-supervised student Asaf Dana. Thank you very much, and please feel free to contact me.